Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 5. We're discussing about the various crystal structures and started with the body centered crystal structure. Here in this particular case we obtained that you have a unit cell which would be which would be able to predict based on the lattice constant the radius. Let us do the similar kind of a thing for the face centered cubic structure as well, which is represented here. In the face centered cubic structure you have half contribution of the atoms at all the 6 faces of the cube, and then there are these 1/8 contributions of the atoms of the corner, which results in the building up of this unit cell recorded as face centered cubic structure. So, here as you can see, the diagonal length of one of the faces is composed of r plus 2r plus r, that is 4r, and this results this actually can be recorded as the diagonal, the face diagonal of a cube of size a, which is nothing but a root 2, okay. And so the r can be correlated to the lattice constant a by just dividing the a by 2 root 2. So, that is how you can constitute the face centered cubic structure. A similar behavior can be obtained for the hexagonal close packed structure. So, here the each plane of the hexagon would have 6 atoms, and there would be a central atom which is in that particular plane. So, if I just look at one of these hexagonal faces built up here, let us say, and these are faces of a regular hexagon, and when we were talking about just a interconnected vertices of such a hexagon. So, obviously because it is a regular hexagon, the angles that these triangles would formulate are all 60 degrees, and they would be lateral triangles and each of them has a unit cell size a, as can be recorded here in the close packed hexagonal structure. And so, obviously the total amount of distance that you would have between this and this atom is basically r plus 2r plus r, that is equal to 4r, and this results in, because it is a equilateral triangle, all sides are equal, this is equal to 2a. So, obviously the r becomes equal to a by 2, and similarly I would like you guys to find out what is the c value which is between these different planes of the materials or these atoms. So, having said that, you have looked at the hexagonal close packed structure, and you have also looked at the face centered cubic and the body centered cubic structure, and how the atomic radius can be mapped with respect to the lattice spacing. Let us look at some of the materials commonly available which can be classified into the various structures we have discussed. For example, material chromium, tungsten, vanadium, molybdenum, iron. There is obviously one temperature range of iron in which it formulates the BCC. Similarly, in the temperature range, in a different temperature range, it can result in formulation of a face centered cubic. Some other materials are aluminum, copper, lead, nickel, silver, which are actually the unit cell is like face centered cubic. Iron, of course, within this range 910 to 1400 degrees formulate a face centered cubic structure, whereas any other temperature range it is actually more like a BCC or a body centered cubic. So, such materials do exist where there are more than multiple crystalline states, and particularly in case of iron, it is more temperature specific, that the FCC state gets formulated in a certain temperature range in which the iron can be kept. So, those materials are known as allotropes, where you have more than one such crystalline states which are possible. There are many other there are other materials which can be again classified into the third close packed hexagonal structure, like titanium, zinc, zirconium, magnesium, cobalt, so on and so forth. And so with this, you get to know a feel of or you get a feel of what are the different classifications of the commonly available engineering materials in terms of their crystal structures. So having said that, now let us look a little more into the aspect of what this crystal structure is at ab initio and how it gets started or formulated. So the atom is always, as you know, in a flowable state, and there is a liquid metal where the atoms have very less bondage because of the high thermal energy or the high kinetic energy of the atoms with respect to each other. So as this liquid metal solidifies by cooling, the atoms arrange themselves in regular space lattices, formulating the crystal. As you can see here, the crystals are just about starting to take place. So such centers are known as nucleation centers, where this nucleation center is basically the start of the activity of solidification and regularizing of the unit cells. And these centers are many across the whole liquid stream. Whenever there is a temperature which comes to the solidification point, and that can be anywhere within the liquid matrix, there are development of these small centers of crystal growth. Unfortunately, the crystals are growing because of the randomness of such nucleation sites or centers in all possible directions, and therefore there are definitely some at some point of time the crystals would go against each other. For example, in this case the crystal is growing in a different direction, as you can see from this nucleation site, and the crystal from this nucleation site is going in a different direction, and they are going to sort of face each other and not be allowed anymore to expand in the regular direction. And so therefore you formulate limited growth long range order areas, which are also known as the grains, and the boundaries where these, because of the randomness of the directions of this arrangement, the boundaries are really those points where growth is no further possible because of the limitation of the other boundary which has come very close, and that point is really where you have the grains and grain boundaries, just as in a polycrystalline material. So I have already discussed that most metals have only one crystal structure, but a few can however have more than one. So those are known as allotropic materials. And so the reason again what we are why we are trying to study this different kinds and unit cells arrangements or crystal structures is because the material strength or some of the other material properties, be it electronic or mechanical, they would heavily depend on the overall crystal structure. So let us study one system of materials which is very commonly used in microelectronic fabrication, and they are like silicon, and as you know that silicon is a very widely used material. Most of the silicon and its compounds, like let us say oxides, nitrides or polysilicon, they can be they have a variety of different layouts, including spanning from crystalline, single crystalline to polycrystalline to amorphous range, and they can formulate a very suitable material for the electronics industry. So you have again some of the materials like let us say oxides of silicon, etc., which are completely amorphous state where there is no long range order at all, or just single crystalline or polycrystalline silicon, also commonly known as poly, are again two different structures, where one there is a repetition of the BCC body centered cubic cell, and the other the polycrystalline structure is for particularly deposited silicon, etc., through LPCVD or PECVD processes, and I am going to touch upon these things later on when we try to cover some of the microelectronic material. But the idea is that this is a system which is very commonly available in all the three different forms of crystal structures. And in single crystalline material, almost all the atoms in the crystal would occupy regular positions, as we had talked about as lattice sites, and because of that the the silicon becomes a very useful material, particularly for the microelectronic applications. So the if we talk about crystalline orientation of silicon and its surfaces, typically the classification would be based on something called Miller indices as shown in the figure here right in this corner. And in the Miller indices, if you want to represent the crystal direction, particular direction would be indicated with the square bracket like 1 0 0. For example, in this particular plane the 1 0 0 direction would be 1 along the x axis, 1 along 0 along the y axis, and 0 along the z axis. So, this direction right here in this particular direction, the x direction is called 1 0 0. So, you have to represent that by a square bracket. If you wanted to represent a set of equivalent directions, it is described by an angular bracket. Say in a crystal you have many such unit cells or lattices, and you have to describe commonly what is the 1 0 0 direction. So, you would actually make a angled bracket in order to represent that, and if this direction is normal, is the normal vector of a plane, that is denoted by the parenthesis this 0, the circular bracket 1 0 0. So, direction represented by square brackets, set of directions represented by angular brackets, and if you wanted to represent the plane that is perpendicular to the direction 1 0 0. So, the plane that is perpendicular to the direction 1 0 0 is shaded plane represented here, right. So, that is the plane perpendicular to the 1 0 0 direction, and so this plane is now recorded as circular bracket 1 0 0, and all such kind of planes would be then represented by these braces 1 0 0 as the third bracket, and that is a representation in which the planes, the directions, and the group of directions and the group of planes are represented respectively. The single crystalline silicon is mostly fabricated with Czochralski's growth method, and I am going to touch upon this method and trying to do some maybe thermal model to illustrate that what are the operational parameters which need to come out, particularly while growing such a matrix of highly purified silicon material. So, the other method is obviously the float zone method, which we will be maybe discussing later on, where there is a polysilicon rod which is heated and converted into a single crystalline material, but then we will start with the Czochralski's growth. So, the Czochralski crucible is represented here in this particular figure, which is really a vacuum chamber where first of all you evacuate and then you flow a inert gas, so that there are no reactive constituents available in the crucible. The crucible here right about in this particular place is really a graphite cup, and it is loaded with polysilicon material, and you have to heat the walls of this cup, so that the silicon, which is the polysilicon which is here, gets converted into liquid melt. Okay. And what happens step by step is the following, that a small seed crystal with a given orientation is dipped into a highly purified silicon melt. You can see the seed being dripped in this direction. The seed was probably somewhere here, which started this whole activity of the crystal, and what really happens is that the seed is slowly pulled out of the melt while the crucible containing the melt is rotated. So, the crucible is rotated and the seed which is being pulled out is pulled out in perpendicular direction to the rotation plane of the particular crucible. So, what is going to happen is that depending on the relative velocity between the the direction of rotation of the crucible and the, let us say, the rotation of the seed, okay, there is going to be a difference in the way that the melt would adhere to the surface of the seed. Okay. So, therefore, when a foreign object is now, a solid object is immersed into this liquid, obviously there is going to be forces of cohesion and forces of adhesion. The forces of adhesion are going to be between the melt and the seed, and the forces of cohesion are between the melt molecules as such. And so, therefore, if we can utilize this clinging to the surface phenomena based on the various speed of rotations or the dwell times, because on one hand you are pulling the seed out, so you are trying to bring it to a lower temperature, so solidification would start happening, and on one hand you are actually trying to limit the amount of dwell time by increasing the rotation speed of the crucible. So, there is a behavior of this material to formulate different diameters, okay, on as a result of this process delay as opposed to the rate at which the seed is being pulled up. And so, therefore, there can be various diameters of solidified material, and the solidification has been initiated by that central seed crystal, which already has a certain direction. Okay. So, this process therefore converts the polycrystalline silicon, which is actually 99.999% pure, very highly pure polycrystalline silicon, into the direction which the seed has, the crystal direction that the seed has. So, therefore, that brings you a bowl of the material here. The material is being evacuated, you can see the moment it comes out of it, it becomes solidified. So, this particular material is actually the solidified bowl. They are all grown in the direction same as the seed crystal, and so there is a single crystalline growth within this particular bowl. So, the seed crystal obviously is a small chemically etched crystal lowered into the contact with the melt, and this is always supposed to give direction, and this must be carefully oriented, since it will serve as a template of growth of the much larger crystal. So, therefore, a slight misalignment in the orientation may result in a different direction of growth. So, one has to be very careful about this Czochralski's growth process. So, if I looked at the one dimensional thermal transport in this such a system, we would like to look at particularly this zone, which is semi solid, semi liquid, and then let us assume that the temperature below this particular zone is the temperature of the melt T1. Okay. So, I will just say melt temperature, and T2, which is outside, let us say atmospheric temperature, which is much lower than the melt temperature. So, T1 obviously is much higher than T2 in this particular case, and therefore, because of this temperature gradient, there is going to be a heat flow across this particular boundary from liquid into the fusion zone, into the solidification zone, and then there is a heat outflow from the solidification zone into the solid metal, which is Q2 dot. So, there is a rate at which heat is flowing in to this zone of, you can call zone of fusion or zone of solidification, and there is a rate at which the heat is flowing out from this other boundary here, which is from the zone of fusion into the solid material. So, obviously, the amount of heat transport Q dot x would depend on the thermal conductivity of the material, the area of the interface, and also the temperature gradient dt by dx of the material, and obviously, the direction of heat flow in this particular case would be from the higher temperature. Direction of heat flow is from T1 boundary to T2 boundary. Okay. So, having said that, let us assume completely one dimensional flow. And you can actually record the heat flow to be KL minus KLA dt by dx of the liquid side, which is actually the heat flow because of the liquid into the zone of fusion, this particular boundary, and the thermal conductivity here is the thermal conductivity of the liquid on this particular side, and this minus the the heat transport across the other phase from the zone of solidification to the solid side, where the thermal conductivity determinant of the heat flow would be that of the solid KSA dt by dx, which exists in the solid side, and this really would be determining the amount of heat which is trapped in order to build the solid material, which is also known as the latent heat of solidification in this particular case, times of dm by dt, which is actually equal to the rate of the formulation of the solid mass. So, you can see that this is the really the thermal balance which is created across the zone of fusion, and we can just indicate this here, just a small section as the zone of fusion, the liquid phase, zone of, you can say, solidification or melting, as you look at it, and then you have the solid phase. Okay. So better known as zone of fusion actually. So A is the area of cross section which we can assume to be equal in all these cases. So A is the cross sectional area. We assume that this is quite uniform, this particular area. So A is the area, A is the cross sectional area, and so of the zone of fusion, and so therefore the equation can be further modified as Ks A dt by dx solid minus Kl A dt by dx liquid becomes equal to L times of area times of the rate at which you are pulling. That is the way that the volume is emerging. So this is the rate of the volume of solid mass times the density, which gives you the rate of mass which comes out of the solid phase. So you are basically representing the dm with rho a dx, and that brings you to a point where the LPA, obviously L rho a dx by dt is equal to Ks A dt by dx s minus Kl A dt by dx L, and further the A can be taken off. I can say that the maximum pull rate here can only be if the liquid side, this conductivity, this value becomes numerically 0, and so the maximum pull rate dx by dt maximum can be in accordance with Ks by L rho dt by dx solid side. Okay. And I am going to talk about this in the next module. In the interest of time, I am going to close this particular module. In the next module, we will discuss about the pros and cons of what happens because of this formulation, and how the maximum pull rate would really depend on the temperature gradient. But on the one hand it is temperature gradient, on the other hand it is how much temperature gradient you can maintain, because otherwise there may be thermal warping and all sort of changes in the crystal. So we are going to discuss this topic in the next module. As of now, let us close this module. Thank you.